last 23 years, I've been on and off a professional programmer, data scientist, algorithm developer, a bunch of other technical fields, and been exploring computational math recreationally and professionally.
So you're one of these people that since you were like a child, you were fascinated with math while everybody else was like sleeping. You were like in the numbers, like you just got it right.
Yeah, I found that it came easier to me than to most, and I also found that um, when you looked, there's shortcuts all over the place. So one of my earliest school child memories was counting exercises, which I was the fastest in the class at. But the worksheets had rectangular arrays, and I noticed that when I brought my worksheet up to be graded, the teacher was counting across and then down. So for a 15, she wasn't going 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. She was counting 1, 2, 3, 1, 2, 3, 4, 5, and checking that it was 15 that way. And so I was like, oh, well, that makes sense that you can sort of, because they'd done counting by numbers and stuff. And it's like, okay, yeah, so that's actually multiplication and you can memorize things that way. So then that instantly boosts you like 3 years because they don't actually make you memorize the times tables for a while after kindergarten, back when I was a kid. And so those sorts of things just keep happening over and over again when you look into them.
So you were fascinated by the idea of finding shortcuts, making things easier, and
I was
or
more fascinated by the idea of things making sense, and that things making
mm,
sense were were sort of almost automatic or trivial.
so somehow it satisfied you in some way the fact that math was so that it just kind of a perfectly uh, you found that kind of some logic in there that resonated with you somehow.
Absolutely, yeah. That's one of the things that's so fascinating about mathematics is that in spite of wildly different approaches to apparently very different fields, so logic, which seems to consist of sort of English or languages-ish things, and geometry, which is about shapes. And geometries can be in 2 dimensions or in multiple dimensions or in weird, twisty dimensions that we can hardly even recognize or visualize, or in arithmetic where you're dealing with numbers, um, or calculus. Nevertheless, the conclusions in one sphere are always recapitulated and confirmed by those same conclusions in every other sphere, and vice versa. And so it's this weird thing where statistics has pi in it, which is the ratio of a circle's
Mm.
circumference and diameter. Um, so just counting things up and keeping track of how many things you encounter uh, connects you to calculus, which allows us to describe engineering and astronomy, connects you to Euclidean geometry, which in one sense is a kind of thing about shapes and forms, but in another sense is this entirely synthetic and abstract space. Um, there aren't any Euclidean planes anywhere because
Euclidean geometry is the basic geometry, like the triangles and shapes like that, or what is it exactly?
yes. So Euclid wrote a book called The Elements, um, and some work has been done in the intervening few millennia since he wrote that to sort of make it all rigorous. But it's basically pretty solid, and he takes 5 basic assumptions and a couple of or 3 sort of core definitions. So he says there's these things called points, there's these things called lines, and these things called planes. And I'm not going to really tell you anything about them. They're going to be described sort of in terms of each other. And then there's going to be these rules for how they can be related to each other, and these basic postulates.
And
And
I got chills, man.
from
This guy
these,
was, yeah. Go ahead.
Yeah. Sorry. Yeah. He derives the ability to construct triangles and pentagons and the Pythagorean theorem and bisections and all sorts of other constructions that are possible, that are all true, that they have to be.
But what year was this? What year was Euclides was?
Euclid was Greek, and I think it's during the sort of golden age of Greece, so it's somewhere in like 300 to 500 BC.
Wow.
But I'm not entirely sure exactly how old the elements are.
Wow. So this guy was just the Einstein of his time. I mean, I mean, to come up with all this in those times, I mean, it's just insane genius, right?
Well, there's a number of insane geniuses to which we owe a great deal from times not quite a contemporary of Euclid, but Archimedes, who's perhaps famous for jumping out of his bath and running naked down the street, for realizing that buoyancy is a thing, and that therefore you can determine whether or not a crown has actually incorporated all of the gold that you gave a jeweler to make a crown for you by weighing the gold and then weighing the crown and confirming that it's the same weight, but also dunking the original gold bar into a fixed depth of water and seeing how much water it displaces, and then taking the crown and putting it into water and seeing that it displaces the same amount to confirm that the density is the same. So that's one of his things, but rather more importantly, he invented block and tackle. And this
What's
is
that?
so if you have a pulley that is a rope going over a wheel, you can redirect force. So you can turn a pull down into a pull up, for example. If you take the end of that rope and attach it to a floating bar that has other pulleys on it, so that these pulleys are essentially pulling themselves together, kind of like the laces on your shoes. You get this arrangement where the force that you're exerting is actually bringing those two bars closer together. And so you multiply the amount of force that you can exert. So he was working for the king of Sicily at the time. And at that time, boats were built on the beach. And when a boat was finished, you'd round up all the big strapping lads in the village, and they'd go down and kind of put their shoulders into it and push that sucker back out into the ocean. He had a pile driven into the sea and basically set up a pulley arrangement between the piling and the boat, and personally launched a boat by standing on its deck and just pulling a rope out through and sort of shrinking that distance by multiplying his own force. And this was something that humanity hadn't discovered yet. And the pyramids, for example, are, thousands of years older than that story. So the great ancient constructions like the pyramids or the Colossus or even Stonehenge were built without the benefit of block and tackle.
Yeah, I mean that's a huge mystery in and of itself. So, so you I want to go back to your a little bit to your childhood. Um, I want to ask you: do you come from a family like of really smart people? Does your parents have some inkling to math, or I'm just curious?
So we're generally pretty bright. My parents didn't go to college immediately. My dad did 1 year and then dropped out. My mother didn't go, but after she had a couple of us, she went back and became a nurse. So they're working class, but books were a more or less constant part of my childhood, and several of my parents' siblings either did go to college or managed to put themselves through high level careers. My godfather, who's also my uncle, actually worked at Fannie Mae, and didn't go to college, but worked his way up, and became an accountant and became an executive at that firm.
So it runs in the family, right? I've always thought that it's but so I want to go back to, so you started kind of, I want to talk about kind of your journey, because you have a personal journey and connection to math that most people don't have. You've through since you started in school, you started feeling some way about math, started enjoying doing, learning about math. And it kept going throughout your life, where I imagine you started getting more interested in more complex math, or kind of how has it evolved your relationship with math and over time?
Uh, well, yeah, basically that was it. My schooling, I was relatively fortunate from seventh grade on to be part of an ever accelerating program to advance the rate that math education happened in my city. So I was one of a handful of pilot children to see whether or not they could start skipping people in grades. And it turned out that they could. Then I started going to UVA while still in high school, because I had completed the math that they actually had. The acceleration program was so quick that they basically didn't have the end of the program ready for us trial kids. So they
Blazed right through it. Wow.
they sent us over to college. And so then UVA introduced me to a lot of other sorts of analysis and algorithms and other things. In nuclear engineering, I was more focused in the calculus and statistics end of things. But then it turns out these days, math is the core. Computers are quite literally mathematical machines. That's what they are and what they do. And so
Coding is just math formulas in words, basically.
yeah. It's been made easy enough that most coders don't think about it that way, which is rather unfortunate. But that's actually what's going on. I was talking to a friend of mine about one of ChatGPT's tricks for sort of giving themselves a database. Because ChatGPT isn't large enough to sort of contain like all of Wikipedia or all of the internet. But the way that it works is by essentially computing these very large number array values from text, which it can then use. If it's got some text, it can use that number array as a function to compute what the new text ought to be, which is how it generates the answers that you see. So what they did was they took sort of large numbers of corpus, Wikipedia articles, I assume, but a bunch of other stuff as well. And they would run it through this and come up with these large arrays of text and use that to generate this 1,000-dimensional vector. So a vector is basically just a sort of arrow in some kind of space. So if you've ever pointed and said, oh, it's right over there, you've given the direction, and then over there is a bit vague, but you've given a distance. If you point and say, oh, it's 50 yards that way, that's a vector. Now, if you're doing that in sort of your normal day-to-day, that's going to be pretty much a two-dimensional vector. Most people aren't saying, pointing up into the sky is telling people to get something. But if you're dealing with, in astronomy, if you're trying to point out to a child where a meteor shower is happening, that might be a three-dimensional vector. But you can keep going up in dimensions. Dimensions are just sort of listed numbers. So they have these 1,000-dimensional vectors that they can plot these things into. The trick is, just like two people trying to point out some particular star will both point in pretty much exactly the same direction, whether they're close or very far from each other. there's ways to sort of compare these vectors to each other that's very efficient. And so what it can do is it can take a request in, generate one of these 1,000-dimensional vector things, and then do a very quick scan of which of these directions are the closest to its database. And then internally, it can take the text of those things and attach it as sort of contextual information. So if you asked it about, monkeys or something, then it could go in and find the 5 internal articles it has that are best keyed to whatever kinds of monkey requests that you made, and then have a lot of local data for itself when it's generating the response to you that it doesn't then have to have stored up inside the big old mess of its sort of AI mind, if you will.
So each array is like a line of text.
Yeah. So a dimension is essentially a sealed off information uh, thing. So it's very hard to visualize these things visually. But if you think about old school audio boards that have sort of different rheostats for different instruments, or if you imagine listening to mixed sound, so imagine you're listening to a 4-part band, but you're listening not to the recording, you're listening to the mixer. So they can turn up or down any one of those parts of the band. The space that you are in as the listener to this is a 4-dimensional space, because the drum can go further away or closer to you without the other 3 changing their orientation. And so can every other sound. So that's what's known as orthogonal, or at right angles. It doesn't change anything to move away from one of them to move away from the others. If you were physically in a recording space with them, that would be impossible. There'd be this kind of mix up of the different things where if you started walking around, the bass might become louder as the vocalist became softer because you were moving towards the bass and away from the vocalist. But you'd also have some sort of complicated relationship with the drum and the lead guitar, say. And the only way to keep a constant distance would be to sort of be walking the circumference of a circle around one of the instruments, which, since no 2 instruments could occupy the same center of the same circle, would mean that you'd be undergoing some kind of constantly changing distance relationship to the other players.
Wow, that's a lot. But so yes, it's a prediction based system that I was trying to understand it. I asked it to explain it itself to me. That it was like it gives from what I understand, my much simpler understanding that was basically like it gives each of those it predicts, it gives you the highest probability of the next thing, that it kind of builds on itself based on all this data that you're saying, on how like basically just gives it everything at a value. So it's like, this is higher value than this, so it's more probable, and that's kind of, it just grabs the highest probable thing, which turns out to be like almost always like the one, almost always accurate, something like this, right?
More or less. So it's basically trying to find a strung together set of words that minimize a certain function that it has. And so if it were to say the sentence, then having the next word be cheese would sort of give it a lot of, that's very unlikely. So that it really doesn't want to do that. If it were to say, this is how I make sense of things, that would make a lot of sense of things, and that would give it a very low score. This can cause some very bizarre behavior in highly technical settings, because in highly technical settings, the words become very, very, very important. If you're just hanging out with your buddies and you're talking about the weather, or, the game, or, the traffic, and somebody says, car when they meant bus, they're both vehicles. It's all kind of the same thing. It's okay.
Mm,
And if your buddy says while he's talking about that play he saw last night in the game, that's not that big a deal. But when you're doing a technical exploration, each word becomes very, very important. And so trying to find the best fit word, it can go awry. But the weird thing is it will generally come back. So it might get the sense of a word incorrect when it's going through a multi-page proof to tell you like how to prove something about calculus is true. But since it knows what that entire proof roughly looks like, while it might call an H and I, for example, because some fields of mathematics use H and some use I to describe certain things, it will, that coin flip might go wrong once, but then it might come back and start doing it again correctly later. And so it turns out there's sort of these patterns within human language, and that's what this particular approach to AI is very good at, is finding what that pattern structure is, and then sort of just like water, rivulating it up and finding where the low path is. It's doing things like that.
wow. So I want to move on to talking a bit about math, because I heard you speaking in other podcast and you mentioned in this one, how every single branch of math connects with every other one and overlaps. And can you talk about that? Because it's really crazy to think about that.
Well, yeah. There's a famous essay called "The Unreasonable Effectiveness of Mathematics" that goes into that, because there's quite a lot of pure math, which has no attempt at effect to the outside world. I was just brushing up on a thing called Coxeter diagrams. And Coxeter diagrams are ridiculously abstract. They're basically just circles with lines between them. And what they describe, in one sense, is certain combinatoric functions. So that would be character strings. So if you have characters, let's say you only have one character, A, and your character strings are just A or AA or AAA or however many A's. And then you have rules for how to collapse these. So two letters of the same next to each other you can collapse. Well, if you only have one character and you have that rule, every character string is the same. Every character string is just a single A, because no matter how many A's you have, you can collapse it back to one A. If you add a second character, not every character string is the same anymore. You can have A, you can have AB, you can have B, and you can have BA. You've got 4 different character strings. So the Coxeter systems basically describe every single different kind of combinatoric character diagram that's possible. But that's not all they do. It turns out they also describe a wide variety of what are known as exceptional finite groups. And one of the exceptional finite groups it describes is something called E8, which you wouldn't likely have heard of. But there's a guy named Garrett Lisi who, about 15 years ago, in what ultimately turned out to be a failed attempt, became globally famous for claiming that E8 was the fundamental group structure of all of quantum physics. And it took the quantum physics community a few years to actually work through the math well enough to disprove that everything fit together quite as well as he said it did.
But it was close enough that took a long time to...
Close enough that it took a long time to get done. And E8 turns out to be connected to a lot of other parts of mathematics as well. So a lot of people wanted it to be true because this very, very important group would turn out to be connected to this very, very important physical theory. It turned out it wasn't quite. There are other groups that are connected to that physical theory. It just turns out that E8 couldn't be one of them. But the Coxeter diagram of E8, which when visualized geometrically is this, like, I think it's a 127 dimensional object, is 8 circles, 7 of them in a line, and 2 in, 1 coming off at a little Y junction. And that's it. That 8 dot connected up in that fashion describes the set of E8, this slightly asymmetrical but still symmetrical enough to be interesting, enormously dimensional object that actually looks almost exactly like the way our universe is structured, but not quite.
Wow. Well, I mean, it's gonna be more complicated than that. I think too, there's probably so much levels of math that probably go almost infinitely deep that I don't.
They go actually much further than infinitely deep. I was on another podcast where I went through with the hosts and taught them how to count past infinity. And there's an entire structure. This was very big in the late 19th century. An entire structure of set theory talking about transfinite sets, which introduced something called the diagonalization argument, which here's a basic piece of math that people don't get to learn about: the pigeonhole principle. You ever heard of this?
No.
So the pigeonhole principle says that if you have a collection of things and another collection of classifications of those things, and the set of things that you're classifying is larger than the set of classifications that you're putting them into. So, like, all the animals on Earth and all the names for species on Earth, there's more animals than there are names for species. So the pigeonhole principle says that if this applies, then at least one classification has to have at least 2 elements in it.
2 elements? You mean 2 units?
So if we have our set of species, which we do, we've got names for the species we have names for, and we have every animal on Earth, then if we start applying those names to all the species, then at least one species will turn out to have at least 2 animals in it.
Well,
of course.
yeah.
So yeah, this seems very simple and obvious, but it turns out that when you're dealing with mathematical objects that can be sort of incomprehensibly enormous, the pigeonhole principle can allow you to be assured of this doubling up. And so one of the more surprising outcomes of the pigeonhole principle, you said you're coming from Mexico. Are you in Mexico City?
I meant it's a town called San Miguel.
Okay. Well, Mexico City has a population in excess of 10 million. The number of hairs on the human head is generally under 100,000. This means that there must be at least 2 people in Mexico City that have precisely the same number of hairs on their head.
That's because sorry, I kind of blanked out. So it's because the classification is
How many hairs? So the classification is how many hairs does a person have on their head? And then the classifying group is everybody in Mexico City. Since the classifying group is larger than the classification size.
Oh, yeah. Well, of course, it's like a riddle. One of my aunts told me when I was little that made me feel so stupid. She's like, if there's 10 socks, how many socks do you need to pull out of a drawer to make sure you have at least a pair? And I was like 11 because they were only black and white.
Right.
And I was like 11, and obviously it's 3.
Yes.
So it's kind of similar to that, right?
Right. Yeah. It's the same kind of trick. And the pigeonhole principle, sort of turned on its side, gets you the diagonalization argument, which is essentially that if you're trying to go the other direction, if you're trying to create a classification of a set that's larger than the size of your classification, then you have to be leaving stuff out.
Okay, say that again, please.
So the way a diagonalization argument works is you're not trying to, you're trying to create this one-to-one relationship between two things, but the second thing is bigger than the first one. And so because the second one is bigger, you'll sort of use up everything you've got, and then you'll still have things left over to classify, so you'll never get to them. And while this makes perfect sense in the finite sense, what diagonalization gives us is the ability to do this to talk about infinite sets. So, for example, you can't create a direct connection between, say, the counting numbers 1, 2, 3, 4, 5, 6, and like that, and the numbers between 1 and 0.
Why?
Because it turns out that in a mathematical sense, there are more numbers between 1 and 0, the continuum it's called, than there are counting numbers 1, 2, 3, 4, and so on.
Because just but because of the decimal place can go infinite, but I mean,
Correct.
number can also go infinite. So what's the difference?
Well, that would get into the technicalities, but it turns out that there's an infinite number of infinite ways that things can go infinite. And the way that the 1, 2, 3, 4 numbers goes infinite is known as countably infinite. And that is the smallest way in which things can go infinite. And the continuum, there's a sense in which that's the second smallest way in which things can go infinite. There's some other assumptions you can make that would make it slightly different from that. But if you use the sort of most commonly used set of assumptions, it's sort of the second most infinite set. And because it's more infinite, if you will, than the numbers, the counting numbers, you will always run out of counting numbers before you run out of decimal numbers between 1 and 0.
So what I'm getting at right now, kind of getting a peek into the math of modern age. When did people or the math community worldwide start to get to these huge numbers and infinites and multi-trillion dimension? Like, is this kind of new, or when did this start happening?
Some of these things are surprisingly old. Some of them are pretty recent. The entire notion around transfinity was, like I said, that was late 1800s was when these things were starting to become a big deal. Starting to think higher dimensionally goes back a bit more than that. Vector's understanding is mid 1800s, and higher dimensional thinking around some of these things goes back a bit more than that. There's some work on different kinds of geometries back into the 1700s and so on. But there's some other senses of some of that work that goes back quite a lot further than that. You can frequently find, echoes of these ideas in ancient writings from Greece or India or China, where they didn't quite have the notational advantage that we have. Modern mathematicians and even modern school children are sort of earning the efforts of thousands of years of trial and error and what the best way to write down these ideas is, because these are very complicated things in many cases, and they get a lot more complicated when you don't have appropriate figures for them. So the Greeks, for example, had this very visual style with geometry sort of being dominant, which gave them a lot of advantages in some places and a lot of disadvantages in others. From what I've seen, ancient Indian writings were very much the reverse of that, where having everything written out in text was sort of the only way that things were done.
Like formulas, numerical formulas.
Numerical formulas and so on, yes. And so, as a result of that, the Indians did way more with numerical formulas than the Greeks did. And the Greeks did way more with geometrical construction than the Indians did, because the Greeks were thinking about everything in terms of geometrical construction, and the Indians were thinking of everything in terms of numerical formula.
Wow. And then suddenly, as the civilizations advanced, like there was a bridge where they connected kind of their
Well,
knowledge together.
for the West, the major advance came during the Renaissance, when as the Europeans were sort of coming out of the Dark Age and were finding ancient texts and recopying things and relearning things, and basically discovering that thousands of years of very intelligent people had had a lot of incredibly bright ideas, then it was a lot cheaper and easier to go look up their bright ideas than to try to have bright ideas of your own. And because they were gathering from these libraries that had been accumulated over centuries and from different parts of the world, and ultimately as they started to trade an expansive part, they were able to bring in things that had been written down in the Muslim empires, or found in attics or so on, and start synthesizing these things into these sort of pan cultural versions. So the number system that we use is based on the Indian number system, whereas the geometry system that we use is based on the Greek geometry system.
Wow. But they basically discovered it, right? Like they didn't really invent it. Like they basically just discovered.
That I am sympathetic to that point of view. There's debate within the philosophy of mathematics about its status as an object of discovery or invention, whether these things exist outside of the minds of the people having them and talking about them, or whether they are just these inventions of random people. One area that I'm kind of looking into right now is something called limit object. So the notion is that if you do very, very large numbers of random things, you will actually converge on something. So, for example, the one that people are most familiar with is the normal curve. If you roll dice, maybe you roll high, maybe you roll low. If you roll lots and lots and lots and lots and lots of dice, you start rolling basically average all the time.
I love large numbers, right?
Exactly. And so that's happening because there's this limit object, this bell curve that these distributions are heading towards, and they're heading towards that distribution quickly enough that they basically get there within our experiential time. But there are a lot of other infinite shapes or infinite structures that random systems can move towards. And this is a problem I was actually played around with a little bit in college. There was a dice rolling game where you rolled a certain number of dice and then you got to pick the highest ones. And those curves aren't normal, actually. There's something slightly different. And that's a pretty important idea. And that's an active area of current mathematics that I just found out about. So I'm trying to study more about that, the structures of what these infinite objects look like. One of the most famous 20th century mathematicians, his number one trick was applying the infinite random graph. So it turns out that if you just take a point and connect it to some of the points that you already have at random, basically a coin flip, and then add another point to the graph and flip a coin to connect them to each, and keep doing that forever. So you have an infinite number of points that are connected to an infinite number of other points. It turns out that if you do that, there's exactly one graph you wind up with.
Wow. Like one structure?
There's exactly one structure that you always wind up with, and it doesn't matter if you flipped a coin or rolled a die or did anything else. If you just randomly build a graph, you will randomly arrive at exactly one infinite graph structure.
So, put that in your pipe and smoke it, right? Like, why? Why is that? That's kind of wow. But I want to ask you because like all these maths are like obviously insanely complex. Like, why I'm wondering like all these mathematicians from the past and even the modern time, like, why are they doing this? Like once you get to the past, like, the simple things that math kind of is commonly used for in the normal world, especially like where there was like no computers, like you were saying they were doing like this crazy math back in the day. Why were they doing this crazy math when there wasn't like any application for for some of this like insanely complicated and abstract math? Is it just out of curiosity? Like they just want to kind of solve it and then later
Well,
the application comes?
some of it,
What's
some
the,
of it is fun. Why do people play professional sports? If you might like playing basketball or soccer or tennis or even table tennis or any other professional sport, um, but you wouldn't need to go professional. You could, I mean, people do these things recreationally. Why do people keep hitting the gym? I mean, you could go to the gym and get yourself in shape, and that's great. But some people keep going to the gym and get really strong, and some people go professional at being really strong, either looking really strong or just physically being huge and enormous and powerful.
Mhm.
Um,
So these old ancient people, like they weren't having like a purpose in mind of why they were like going so deep and uncovering all this. They were
well,
just kind of uncovering it, and or
the,
was it like a purpose
some
to it?
people are like that, but the thing is, people have problems, and people have interests, and people have curiosities, and math is the most powerful mental tool that we have. And so if you have problems that have those sorts of issues, then you'll find that math is the tool that you're going to keep coming back to. There's something called the Poisson distribution. And we've talked about the normal curve. The Poisson curve is sort of the normal version of the curve, but only for when you're counting stuff up. So if you've got distributions that might go, infinitely high, but there'll always be 1, 2, 3, 4, 0, something like that. Well, Poisson actually worked for Napoleon Bonaparte, and Napoleon had a problem. People in his armies got kicked by mules, and he didn't want people in his armies to get kicked by mule because you couldn't really plan for it. It was happening basically at random. And soldiers that got kicked by mules, every once in a while it was okay, but mostly that person died slowly and painfully, which is bad in itself, but is also bad for unit morale, drags down the unit's, supplies and so on, slows things down. You might have to put the mule down if it's figured out that, murdering people is something that's fun, which does even more damage to your supplies. So he wanted to solve that problem. He wanted to be able to predict when people would get kicked by mules. And Poisson was a very smart mathematician, so he put him on it. And Poisson came back and said, "Yeah, I cannot predict when people will be kicked by mules. That looks like it's impossible. But what I can tell you is exactly how many people, what probability in each company, in each army, uh, which counts of people will wind up getting kicked by mules over the course of 1 week or 1 month or 1 year. And this is what the curve will look like." Um, and the phone company uses Poisson distributions to figure out what its capacity figures look like because it's exactly the same mathematics.
So what I'm getting from this is that back then, the fact that Napoleon went to this to Poisson to it was like the mathematicians were seen to have like math was kind of almost like a not that it was like a sorcery, but it was like a something that had a way to somehow predict or solve problems
Well,
that were beyond.
Napoleon, before turning himself into the emperor, was a lieutenant in the French army and in the French artillery. And the artillery back in those days is where you put your smart people, because aiming cannons so that they hit what you want them to hit, don't just fly off into the clear blue yonder, particularly once you start aiming in large parabolas, which aren't parabolas because air resistance causes foreshortening. Um, and keeping track of the gunpowder and keeping it dry and having it in the right place and not having it blow up in your face were all very cognitively demanding tasks. And so Napoleon was a pretty sharp cookie who was no slouch at arithmetic himself. And so he was aware of just how powerful this tool was. And he wanted as much of that power as he could get in his quest to, conquer the world.
So math, and it was kind of going back to almost the way you saw it when you were young, and it's like it's in itself a power to to be used for whatever ends it applies to. It's a tool basically that gives us extra power.
Absolutely. Yeah. It's an extraordinary ability to be able to reason out things arithmetically instead of having to physically move people around to figure out, how long a line's going to be if there's 30 people in it. Um, uh, the that's one of the major reasons why modern engineering is even possible. Um, Bridge building, say 500 years ago, had a certain amount of trial and error involved, and a lot of overbuilt. It's not uncommon to see in places that have civilizations going back this far, footpaths or other small out of the way structures that are hundreds or even thousands of years old. And those paths are incredibly overbuilt, solid stone for virtually their entire thing. But the reason those things are small and out of the way is because those are really as big as they could actually construct things. And things like modern railroad, bridges that can go over vast gorges, or roads, or other sorts of very, very large constructions, or the chips inside your computer have incredibly fine tolerances with incredibly complex interactions among the truss members or the capacitors and transistors and so on. And having to figure out how that stuff is supposed to work by building them and letting them fail until you build one that doesn't fail, and then trying to remember what you did when you built that one to do again the next time, can't scale up to modern technology. We need to be able to write down a plan and test it at the plan stage, and then test that at each stage of building to make sure that we're building to the plan.
Got it. And all this extremely complex math, or I imagine there's like a ton of this math, the new math, all this crazy math that they have like understood how it works. Like they've kind of mapped it out and understood the mechanics, but they have no idea what it's for yet. It's just there.
Oh, absolutely. There's one that actually just entered into the popular imagination earlier this year. There's a team that was effectively instigated by one recreational mathematician who worked out this tile shape called the hat. And the tile had certain flexibility, but it's this 8-sided shape. And if you took that shape and its mirror image, it's flipped over reverse, you could tile an infinite plane irregularly. And while they were publicizing that and sort of basking in the glory of solving this problem of finding a single shape that could irregularly tile the entire plane, the hobbyist came up with a second shape called the spectre, which was even more flexible than the first shape. And it doesn't need to use its mirror image reverse. And so they kind of stole their own thunder, because they solved the next hard problem while they were still being feted for solving the last hard problem. But a tile that you can put down on your bathroom and the patterns won't repeat at any point doesn't have any particular value as far as anybody knows. And so we don't have anything to do with that right now.
It's funny. So some math obviously has a lot. like back then the math was very simple and the application was very simple, and then it gets complex, and then technology comes and they realize that that complex math actually works. So is it it could be that every type of math system or whatever has an application, and if
Um,
maybe
there's
there's
actually a mathematical proof to that effect. So, as it turns out, there's a one-to-one correspondence between mathematical proofs and computer programs. And computer programs, there's a direct connection between computer programs and every imaginable system. And since physical systems are all subsets of imaginable systems, every physical system has a corresponding computer program, which has a corresponding mathematical proof, which means the vast majority of mathematical proofs actually have, or many mathematical proofs wind up actually having corresponding physical systems. And every physical system has a corresponding mathematical proof. So while it is not necessarily the case that uh, every mathematical idea will have a practical application, every practical application has an important mathematical idea.
And I'm wondering, I mean, this is my crazy brain thinking, but what if we're getting to such an advanced math that we're kind of getting into the math of like another dimension, and that's kind of the math is the kind of what we have between us and I don't know, like a much more complex kind of realm or something that only the math we can see of that, and we don't know what it is for.
Well, that's one of the possibilities that's currently being floated for physical grand unification. The guy named Stephen Wolfram, you might be familiar with Wolfram Alpha or Mathematica. Wolfram Alpha is this math search engine online that will answer math questions for you to an incredibly high degree of sophistication. So if you ever have a calculus problem and you don't feel like learning calculus, or just don't feel like doing it if you already know it, you can pop it into Wolfram Alpha and it'll give you a graph and tell you what the answer is.
What's the website?
Wolfram Alpha.
Wolfram Alpha. Just Google it. And
Yep.
Wolfram Alpha.
Yeah.
Okay.
It's popular enough that you might not even need to Google it. The search bar in your browser may well just say, "Oh, you're talking about Wolfram Alpha, right?" I can tell you where that is right now. So Stephen Wolfram is a super genius, and he's got a theory. He wrote a book called A New Kind of Science back in the early 2000s that started exploring this idea that the universe itself is operating on computational principles, that there's some sort of foundational units that are way too small for us to see or detect that are engaged in computational behavior. And the stuff that we can see and detect, like quantum physics and the cosmos, is the result of these very small computational objects computing from their immediate neighborhoods very rapidly. And we need something, because our existing mathematical theories, are you familiar with dark matter or dark energy?
I mean, I've heard about it, but I don't really know too much about it.
Well, basically, what's going on is that we have general relativity, Einstein's theory, which makes great predictions inside of our solar system, better predictions than Newton does, but doesn't make great predictions at the galactic scale or at the cosmic scale. It makes some really good predictions at those scales, but galaxies don't really spin at the speeds that Einstein's theory says they should spin at. And there's some other things happening that don't look the way they ought to look if Einstein is correct. But if 3 or 4 times the amount of matter that we can see exists, and this other matter that we can't see also exists, then Einstein would work out. But then, for the galactic level, mostly. But then at the cosmic level, things are sort of flying apart too quickly, and all that extra mass would cause them to fly apart even less quickly. So if 30-ish%, a little over 30% of the visible universe was invisible matter, and a little over 60% of the visible universe was invisible energy, that's what dark matter and dark energy are talking about, then Einstein would work out. But of course, that would require 90-ish plus percent of the universe to be stuff that we don't interact with and can't detect, which is a bit of an issue. But there's a lot of measurements that make sense if that's true. It's just that being true doesn't make sense in and of itself. And so Wolfram thinks that his approach can sort of bridge that gap. I have no idea whether or not he's correct. And unlike Garrett Lisi, he doesn't. The current engagement is not that high. It hasn't gone sort of viral yet, but I guess we'll see.
But what is his opinion of what is wrong with Einstein's, and what is his, like in a nutshell, what is it, his way? How does his way predict it better?
It really doesn't. He's not really in the prediction space. So the downside of his theory from a scientific basis is that, and that's why his book is called The New Kind of Science. Sorry, I keep diverging. But to get back to the point, computational systems are guaranteed to be able to precisely follow any describable system, because that's what computers are for. They're for doing anything that can be imagined. So if Wolfram is correct and there's some sort of computational substrate of the universe, then no matter what we observe, that computational substrate, there's some programs, and there's many programs, in fact, that will exist that could produce that output, which in terms of grand theories doesn't get you very far, because there wouldn't be a grand theory. There'd be sort of this vast families of grand theories that would all be perfectly reasonable. But if there is this computational substrate, then there could be sort of an exploratory thing. So physics would become somewhat more like biology 300 or 400 years ago, where mostly it was about getting out into the field and seeing brand new things, and less about staying back in the lab and sort of coming up with brand new ways to measure stuff.
Got it. So this system, this concept of Wolfram, is it a? So he's saying that it's the substrate, or this basic kind of fundamental thing that's everything is on top of it. He's saying that is like a mathematical formula or some type of.
His favored explanation is something called a cellular or automata. Pronunciations vary, but if you're familiar with the Game of Life by any chance?
No,
not the board game. Okay, well, essentially the way a cellular automata works is, at the basic level, imagine a line, and the line is broken up into segments, and the segments can either be colored black or white. And so you have a rule. The line can see itself and, say, the two segments next to it. And so there are 8 possible patterns of segments that this line could be looking at. It could be looking at 3 white. It could be looking at 2 whites and then a black. It could be looking at a white, black, white. There's 8 different combinations that it might be looking at. And so for each of those 8 things that it might be looking at, it would then turn itself either white or black. So there would be 16 possible rules in this 3-segment line game. And so if I drew this line out, sort of white, black, white, black, white, black, white, black, 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 white, 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 whatever, draw this line out, then I could draw a second line underneath it, which would be the second iteration of that line. And so I could sort of create this 2-dimensional picture of this line evolving itself pixel by pixel, where each pixel was looking at the 3 pixels above it and creating its new value. And he gets into this a lot in A New Kind of Science. He's actually using not windows of 3, but windows of 5, so he can see 2 to the left and 2 to the right. And he discovered a rule 127, I believe, that within the context of that space was capable of general computation. So it was capable of achieving the same level of complexity as your computer or your cell phone, or like the supercomputers that the Americans and the Chinese are building, that sort of thing, or your brain. And so if this incredibly simple system of just lines evolving over time can exhibit this level of complexity, what happens if you're talking about not a line evolving over time, but a plane or an entire space evolving over time? What if there's sort of three-dimensional? There's more immediate neighbors, and so there can be more complex rules. And the thing is, once you've gotten past the lower barrier of complexity, then you get into this sort of level. There's a guy named John Conway that invented a game called Life that was based on a two-dimensional array with a few rules for how the thing could either turn itself off or turn itself on again. And Conway's a very famous mathematician. He had a obituary, I think in the New York Times, that in its online version had a very famous video where it's focused in on a game of life progressing itself. And you see these complicated shapes undergoing this evolution where they're traveling around and blowing themselves up and creating new versions and other shapes that go off in other directions. And they pull out of this thing continuously, and they pull out effectively millions of X. And what happens as they pull out is that you realize that what's actually going on is that somebody had programmed this game of life to play a game of life. So the shapes are actually recapitulating these incredibly large territories that are acting as single pixel. And that's the basic property of computational systems. Computational systems are capable of encapsulating computational systems. So it is possible to fully imagine and fully realize all of the capabilities of some other system that's also computational.
I mean, it's a lot. But yeah, I mean, these things are very hard too. I mean, it's so complex. To explain simply, it's basically
right. Yes, the fascination is its complexity, but the complexity is so intrinsic that what you're explaining, effectively what's happening is that this is the limiting case. We were talking about sort of these infinite objects that things could start approaching. Computational systems are the limit object of imagination. Anytime you imagine anything, as you imagine, genies wishing for more wishes, as you get crazier and crazier and more powerful and more complicated, you will always eventually run into a fully computational system, and you will never get past it.
Wow. But that doesn't mean we live in a computer system. It just means that
right.
Just means that who knows what it means? It means something.
Yeah, you'll have to talk to somebody a lot higher on the food chain than me to find out what they mean. I'm just trying to work out what things are. Yes.
Yeah, I think God would be a good person to consult on that. Man, wow. So what I learned, I got a picture of how advanced, how crazy math is. I mean, also, the history, just the mystery that is math, that is almost mind. You can go crazy with this stuff, right? Just so, it's like, why is it there? Like, it is mind-boggling and fascinating. And yeah, it's a shame that in school they made math so the way they taught it to us, it made everybody almost repel ourselves from it.
Yeah, I've always found that somewhat regretful. There's math, because it has this property that it has right answers, and there's rules that in many cases really are the easiest ways to do things. There's consequently so much focus on this mechanization this mechanical structure, um, which is vitally important. Like that you there's a lot of different ways to add one to one, but there are no ways that don't arrive at the number two. So this sort of linkage power that it has to be useful across every field of reality and connect to these very different ideas is linked to this fact that it's so rigidly put together. But we really emphasize only the rigid things, and there's so many creative opportunities that are available even at the very basic level. And we teach people who maybe aren't as good as arithmetic but would be better at geometry that the fact that they like to draw means that they're bad at math, when it might mean that they have an entirely new kind of insight that could change how we think about how to think.
Yeah, and I'm thinking it would be really funny, like in the future when they map out all the math in the universe, and then they finally, compute it, and the whole entire universe equals zero. You're gonna be like, what the hell? But I mean, man, I want to learn math, but I don't even know where to start. Like for somebody that's like listening to you and they're like, man, I want to kind of not go to the crazy trans-dimensional, all this like like what does maybe somebody that wants to learn more, is there some books or some specific branch of math that is kind of fascinating, that's not so complex to get a taste for it and learn? What would you recommend?
Well, there in fact are books. There's websites. Uh, Puzzle books can be quite good. Raymond Smullyan and Lewis Carroll of Alice in Wonderland fame both wrote puzzle books to introduce mathematical logic. Carroll, pre-computational mathematical logic, and Smullyan, post-computational mathematical logic. So those are both excellent resources. There's the internet itself, since it's built on computers and computer scientists, they know their roots. There's enormous resources from Khan Academy and other, some paid sources that will teach you math, but also free sources. There's actually a challenge called the Summer of Math Exposition, and I'm pretty sure a YouTube or even just a general search will find multiple videos of people explaining whatever their own private little areas of math are, and doing their best to make them fascinating. Some of them are very amateurish, some of them are very professional, but that's a vast array. And college professors, math professors, not only put their courses online, but in many cases put aspects of their private research online. And if you don't understand it, rest assured, most people don't understand it. So bounce off that one and bounce to something else.
Hmm.
If you do find an area that you're interested in and is starting to make sense to you, one of the nice things about that is that the terminology you pick up will then let you search on Wikipedia or any of these other sites to find all the other stuff, and you can find the terms in those things that don't make sense. So basically, my path for computational mathematics, which I started to learn as out of a sense of professional responsibility, was to take the terms from the book on the programming language that I had and use them in Google to find articles about these things. In many cases, I found the actual mathematical papers where the initial proofs were done. And as I read through those, when I found ideas that I didn't understand or ideas that I found fascinating, I would look those things up and find the papers that explained those things. And it's work, but
Yeah.
going to the gym to be able to deadlift hundreds of pounds is work too. It's very rewarding work.
I guess that the more you understand it, the more it's like anything in life, the deeper you get into it, kind of you enjoy it more. It's like you have more to draw from to think about things.
There's a definite sense where that's true, but the because of math's sort of understanding based structure, the more you understand it, the easier it is to integrate these new ideas. So it at each step of the way, again, much like bodybuilding, when you get stronger, you get stronger, and so being able to lift more one way will ultimately allow you to lift more other ways as well, or be faster or jump higher. Um, as you understand more, you will find you understand more things, and when you see things, you'll be able to see the pattern that they fall into and realize that you have tools to address those patterns.
Basically, like a riddle, or it's basically like a little game, to solve these little formulas and learn this all these different things. Um, like almost a hobby to for some people like yourself. And well, what else I was about to ask you something. Well, let's talk about you basically, and as we wrap up, you know, you basically came up with a way to make efficient. You found some inefficiencies in the commodities markets that you basically put you have a patent pending on it, um, and it's a way to basically reduce costs and make them problem the prices more efficient using math. Um, so can you tell us about that, please?
Yeah, sure. So again, to sort of describe the market from a mathematical point of view, what marketplaces are doing is noise cancellation and signal boosting. So let's say you have lots of people that are all producing one product and lots of other people that all need to use that product. So there's a few ways we could go about this. One, everybody could just make private deals. And some people will be better at making deals, and so they'll get better deals than other people will. And so sort of the predators will seek out the prey, and you'll get a very lopsided market. Some people will be making crappy versions of the thing and selling them for lots of money because they're very good at selling, or the people that made their buyers are very bad at buying. Um, some people will be buying for a lot less than they should be, and the producers will sort of be exploited. And some people will sort of be even. And what will happen overall is that you'll produce less of that stuff and use less of that stuff because some of the prices were too high, some of the prices were too low. With the prices too high, people won't use as much as they should. With the prices too low, people won't make as much as they should. So since everybody's making the same thing, you can have a common marketplace where everybody comes together and trades. And what that does is it sort of creates a common price. But how do you structure that common price? The way we do it is by having that same sort of everybody making deals, but doing it all in public. Unfortunately, computers make those deals so quickly that public is only alive for tiny fractions of a second, too small for consciousness to actually happen in. And so what happens is we see prices sort of bouncing around all the time. And those bouncing prices lead to exactly that same kind of depression of the entire economy. So what I do is I essentially do two stages. The first stage, the people come together and say where they think prices are going to be. And then the system integrates those together into a common price. And the second stage, we advertise that price and see how much people want to trade. But instead of just doing one price at a time, we do all the prices into as far into the future as anybody cares to guess at. And so what we're doing there is we're taking the long term into account during the short term. So the existing system that sort of has to bounce to do that can now be stabilized. And so we have a system where everybody can come together and know what everybody else's price is. And basically you get what you pay for, and that leads to a lot more prosperous economy, because everyone that has a need and can pay for it get the thing that they need, and everything that has the ability, everyone with the ability to produce economically can do so prosperously.
Yeah, and I heard you say something about how by grabbing the average of all the predictions, the average was like so close to the actual uh, price, right? In the future.
Yeah. So there's a well-known phenomenon, that sort of medians of guesses do very well. So this is a thing that can happen at the county fairs, where they'll have like a, guess the number of marbles in a jar, or guess the weight of a bowl, or something like that. And some people guess off, some people guess pretty close. But if you take all the guesses and just sort them out, and then take sort of the average of the guess that's in the middle, then you'll get a guess that as good, or in some cases even better than the best guess in the entire group. And now imagine if you played that game over again after you published that information. So now everybody gets to see where the best guesses are all clumping together, and they get to make their new guess based on that information. And so
It's insanely accurate.
yeah,
Time.
yeah. And you get rewarded for how accurate you wind up being. So
There's an incentive.
everybody wants to agree to what everybody wants to agree to, because that's how they make all their money.
Mhm. So that's kind of the system that you created is a way to do that with the commodities markets.
Yes, yes. To figure out how to agree to these agreements on not one thing, but rather this time looping function of where prices are going to be today and next week and next month and next season and next year. But everybody's still trying to push that towards the point that everybody's going to agree to it, and after everyone's agreed to it and everybody knows what everybody's agreed to, they'll also be able to trade at that price.
Got it. Got it. So I mean, it's a revolutionary system. It it You're the creator of this whole thing, right? You're the father of this whole concept. Or was it a
Yeah.
group of people?
No. I mean, I did all the working out, and I wrote the code. I had a few interesting questions get asked to me, that sort of got me inspired to think about this problem. But aside from that,
Wow. So amazing. That's amazing. I mean, I wish we had more time to go into it more deeply. We covered a lot of stuff. So I guess we can wrap it up. Noah, you can tell the audience, your website, uh, and anything else you want to, tell people about.
yeah, absolutely. So there's a website at coredis.com to talk about this marketplace idea. Or if you have any questions for me, please reach out, noahhealy@yahoo.com, or on LinkedIn. I'm Noah Healy there. Also, I've recently launched a podcast with a guy named Marty Wiener, who's the former CTO of Reddit, called The Fourth Age, the AI Revolution, where we talk AI, where it is, where it might be going, things that we could build if we decide to have a civilization, things that we might be building in the expectation that we are not going to have them. We'll say.
The expectation that we survive all this.
Yeah. Well, there's some crazy things out there.
I know.
But yeah, if you're interested, come on over to the Fourth Age.
No, that's awesome. So either way, I'm gonna put everything in the show notes, but I also like to say it a few times because sometimes the show notes glitch or something I've seen in podcasts. So the website is Coordisc, and it's spelled COORDISC.com. And can you also repeat the podcast as well, please?
The podcast is The Fourth Age, THE, the number four, THAGE, on Google, Apple, Spotify, and other platforms. Um, and yeah, my email address, noahphhaly at yahoo.com.
Awesome, awesome. And it's been so fascinating. And you're making math great again. And I'm sure a lot of people really enjoyed this. And you know, and so you're doing a great service. You're doing great service with the financial thing, with the financial patent. And yeah, I'll check out. Everybody go check out his podcast as well. I mean, that's where you can get a lot of Noah insights and more learning more from him. So Noah, it's been a pleasure, my friend. Thank you so much for coming.
Thanks for having me here. This was a lot of fun.
Yeah, it was a lot of fun, and well, we'll keep in touch, my friend.
Absolutely.